Now we come to another fundamental property of Hermitian operators, namely completeness. In the previous slides, we proved that eigenfunctions of a Hermitian operator corresponding to distinct eigenvalues are orthogonal. If we also normalize them, then they satisfy the orthonormality condition shown here. Now the new idea is the following. In linear algebra, we know that if a set of linearly independent vectors spans the entire vector space, then that set is called a complete set or a basis. In quantum mechanics, the same idea applies, except now our vectors are wave functions in Hilbert space. So when we say that the eigenfunctions of a Hermitian operator form a complete set, we mean that an arbitrary square integrable function f of r can be expanded in terms of those eigenfunctions as shown in this expression, where the expansion coefficients c sub n are in general complex numbers. So the eigenfunctions are actually building blocks from which a general admissible wave function can be constructed. You can think of this as the quantum mechanical analog of Fourier series. In Fourier analysis, we expand a general function in terms of sine and cosine basis functions. Here, we expand a general state in terms of eigenfunctions of a Hermitian operator. And physically, this is extremely important. If the operator represents an observable, then its eigenfunctions are the determinant states of that observable. Completeness tells us that even if the system is not initially in a determinate state, its wave function can still be written as a superposition of determinant states. So arbitrary states can be decomposed into eigenstates of an observable, and those expansion coefficients carry physical meaning. We will discuss this in more detail later in this chapter. Another point that is worth stating explicitly here is that orthogonality does not follow from linear independence alone. For Hermitian operators, orthogonality follows from distinct eigenvalues. So on this slide, the key message is this. Orthonormal eigenfunctions of a Hermitian operator can serve as a basis for the Hilbert space of allowed states. Now that we know a general function can be expanded as a linear combination of orthonormal eigenfunctions of a Hermitian operator, as given by this expression, the next question is, how do we determine the coefficients c sub n? The question we raised on the previous slide is exactly the same problem we encounter in Fourier series. Once a basis is known, we want to know how much of each basis function is present in the function f of r. The derivation is straightforward but very important. Start from the expansion f of r equals summation over n c sub n times phi sub n. Now multiply both sides by the complex conjugate of phi sub m. Then integrate over O space. After applying the orthonormality condition, we can replace the integral shown here by delta sub mn, the Kronecker delta function. And since n runs over all indices only when n is equal to m, while delta sub mn be non-zero, we end up with the expression shown here. C sub m is equal to the integral of the complex conjugate of phi sub m times f of r carried over O space. If we relabel the dummy index m back to n, we obtain the standard formula shown here. The derivation of the expansion coefficient c sub n using bracket notation is shown on the right for your reference. This result has a very simple and important interpretation. The coefficient c sub n is the projection of the function f onto the basis function phi sub n. In Hilbert space language, it is the inner product of phi sub n with the function f of r. So each coefficient tells us how strongly the state f overlaps with the eigenstate phi sub n. This is precisely why orthonormality is so important and so convenient. If the basis functions were not orthonormal, extracting the coefficients would be much more complicated. But with an orthonormal basis, each coefficient is obtained directly by projection. This formula will later become physically meaningful in quantum mechanics. When f is normalized wave function and phi sub n are eigenfunctions of the operator corresponding to some observable, then c sub n is the complex amplitude for the system to be in the eigenstate phi sub n, and the absolute square of c sub n will be interpreted as the probability of obtaining the corresponding eigenvalue upon measurement. Now we move one step deeper. We will derive a very important identity called the closure relation, or equivalently, the completeness relation. Starting from the expansion formula for f of r, and then substituting the expression for the coefficient c sub n, we obtain the expression shown here. Notice that I'm now using r prime as the integration variable so that it is clearly distinct from the external variable, the small case r. Then we can move the summation inside the integral. The above equation is in the form of the general identity shown here, which reduces to the one-dimensional expression that you may be more familiar with. So if this equation must hold for any function g, then the kernel capital K of r prime and r must be the direct delta function, as shown here. Therefore, we conclude that this equation must hold. This is the closure relation or completeness relation. This equation is extremely important. The orthonormality condition involved integrating the product of two basis functions and obtaining delta sub mn, which is the Kronecker delta function in the discrete index space. The closure relation is, in a sense, the complementary statement. When we sum over the basis index n, we recover a direct delta function in coordinate space. Below is the bracket version of the completeness relation, which is actually even more elegant than the coordinate space derivation, because the closure relation is most naturally written as an identity operator, as we will see later on this page. We begin with the expansion formula for the function f, as shown here, using bracket notation with c sub n, the expansion coefficient given by the inner product of the eigenfunction phi sub n with the function f. We substitute the coefficient back into the expansion, we obtain this expression, where we have summation over n of outer products phi sub n ket bra, as shown. Now vector out the ket vector being acted on, we obtain this expression. On the left-hand side, we have the ket vector f. On the right-hand side, we have the quantity within the parentheses times the ket vector f. Since the above equation must hold for any ket vector f, we have the expression shown here, which is the summation over n of outer products phi sub n ket bra must equal the identity operator. Physically, the completeness or closure relation says that the set of eigenfunctions is rich enough to reconstruct an arbitrary state exactly. This is precise mathematical meaning of completeness. This slide gives a visual illustration of the completeness relation. The idea is that the direct delta function can be represented in the limit of infinitely many basis functions by a sum over products of complete or the normal basis functions. In other words, if the basis set is complete, then the partial sums should increasingly resemble a sharply localized delta-like spike. The plot given here shows precisely that behavior. The basis functions here are cosine functions of the form, and the quantity being plotted is a truncated sum of the form shown here, which is equivalently a shifted version of the closure kernel. The important point is not the precise shift by one, but the fact that as more and more basis functions are included, the sum becomes more and more sharply picked near the location where the argument matches the shift, which is at x equals 1. The four approximations shown here use 10, 20, 50, and 100 basis functions. With only a small number of terms, the peak is relatively broad and accompanied by visible oscillations. As the number of terms increases, the peak becomes narrower and taller, and the approximation more closely resembles a direct delta function. This is exactly what completeness means in practice. A finite partial sum cannot produce an exact delta function because the delta function is an idealized distribution. But as the number of basis functions increases without bound, the partial sum approaches the delta distribution. So since the definition of a direct delta function requires an infinite number of terms, the set of eigenfunctions forms a complete set. So the message of this slide is that the direct delta function effectively encodes the reconstruction of arbitrary functions from a complete basis. The fact that the basis can reproduce such a sharply localized object or distribution is a strong indication of completeness.